Hi everyone. Today we're going to be completing our notes on 8-5 linear, exponential, and quadratic models. I want to start off with this example. JC and Emma use different functions to model the value of a bike X years after it's purchased. Each function models the data in the table. So let's take a look at the table of values here and see if we can make sense of what's happening. At year zero, or at time zero, the value of the bike is $500. After 1 year has passed, the value of the bike is $485. After 2 years, it's $472, and so on. Here's a graph of the value of the bike as it relates to the time in years. So we can see the scatter plot that it decreases over time. Okay. JC's function is represented as f of x right here, and Emma's function is represented as f of x right here. So what do you notice about the data in relation to the two functions? Well, I noticed that both of these functions modeled a decrease in the value over time. So one way we can answer this question, this has many different answers. We can say as the number of years increases, the value decreases. Okay? So as the number of years increases, the value decreases. So take a look at each of these functions here and compare and contrast them. How are they similar and how are they different? Well, first thing I noticed is that in JC's function, this is a linear function where the y-intercept is 500. That would be like our starting value. Likewise, in Emma's function, this is an exponential function because we've got the variable and the exponent, where the initial value is also 500. So one way that they are similar is both have a starting value of 500. Okay. One way that they're different is the type of function that they use to model it. So like we mentioned earlier, JC's function is a linear function with a negative slope of 14, whereas Emma's function is an exponential function with an exponential decay factor of 0.85. So that's that exponential base. Okay, so JC's is linear, Emma's is exponential. Okay. So whose function do you think is a better model of these data? Explain your reasoning. Well, let's take a look. I can see from the graph that this looks like it might be curving a little bit, but otherwise it looks pretty straight. I bet if we were to draw a line of best fit, then this would look closer to a linear function, JC's function. Okay. One way we can also test this is by plugging in 1, 2, 3, and 4 in for x in each of these functions. If we do, we find that JC's function aligns more closely to the data points. So an example answer for this is JC's because it stays closer to the data points. Neither of these representations are necessarily worse, or rather, are neither of them are really bad. However, JC's is just a little bit better because it closely follows that data. If we were to extrapolate data from these functions or find data that's not included in the original data set, then JC's function would give us a better or more accurate extrapolation of that data. Okay? So now I want to talk about some of the different ways that we can determine which function type represents data. So given some sort of data, be it a table of values, a graph, or an equation, how can we use all of the different function types that we've learned this year to determine which is going to be the best fit for that data? So the first way that we're going to talk about today is numerically, or using a table of values. In order to determine which function type best represents data in a table of values, we have to consider each function's rate of change. We know that the rate of change for each of the different functions that we've studied this year is different for each of these function types. One way we can think about rate of change is by finding the difference in f of x values between successive changes in x values. So as we increase the x values, what's going on with the f of x values? So for example, linear functions model data where the first differences are constant. Quadratic functions model the data where the second differences are constant. And finally, exponential functions model data where the ratios of consecutive y values are constant. So let's take a look at what some of this means. Go ahead and flip the page. In example 1, I'm given three functions, f of x, g of x, and h of x, and we have to determine which function type each of these represent. So starting with f of x, the first thing that I like to look for is the first difference. So I'm looking between successive terms in the f of x values. What is the first difference? So to get from -1 to 1, we add 2. To get from 1 to 3, we add 2. And to get from 3 to 5, we add 2. And from 5 to 7, we add 2. And so because all of these first differences are the same, we know that this is a linear function. For g of x, again, I'm going to check those first differences. So to get from 3 to 9, we add 6. But to get from 9 to 19, we add 10. To get from 19 to 33, we add 14. And to get from 33 to 51, we add 18. Okay? So these first differences are not the same, so let's check the second differences. To get from 6 to 10, we add 4. To get from 10 to 14, we add 4. And to get from 14 to 18, we add 4. So because the second differences are the same, we know that this function is quadratic. Finally, for h of x, I notice that, well, looking at these, to get from 1 to 2, we add 1, then we add 2, and then we add 4, and then we add 8. So the first difference is not the same, and we would find that the second difference is also not the same. So we have to check, is it a common ratio? If I take any successive terms, do we multiply by the same amount? Well, to get from 1 to 2, we multiply by 2. 2 to 4, we multiply by 2. And each time we're multiplying the outputs by 2. So because we have this common ratio, we're multiplying by the same amount. This is exponential. Okay. Let's try another. Example 2. The owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. Which function type would be used to estimate the cost of the bubble wrap for a picture with length 75 inches? So let's take a look here. I notice that, let's check the first differences. I notice that from 10 to 31, we have to add 21 cents, or 0.21. To get from 31 to 62, we have to add 0.31, or 31 cents. To get from 62 to $1.04, we have to add 42 cents. And then to get from $1.04 to $1.57, we have to add 53 cents. So our first difference is not the same. So the first difference is, I'm just going to go ahead and list all of them. So we had 0.21, 0.31, we had 0.42, and then 0.53. Let's check the second differences. To get from 0.21 to 0.31, we add 0.1. To get from 0.31 to 0.42, we add 0.11. And finally, to get from 0.42 to 0.53, we add 0.11. So the second differences are 0.1 and 0.11. These are pretty much the same thing. It's very close. I suspect that the additional cost of the bubble wrap changes by a single penny just due to rounding. So we can consider these second differences, since they're so close together, we can say that they are pretty much the same second difference. So therefore, because it's the same second difference, we know that this function is quadratic. So the cost of bubble wrap for packing pictures here can be modeled using a quadratic function. All right, go ahead and flip the page. Now that we've talked about how to find the function type from a numerical data set or a table of values, let's talk about finding it graphically. So recall the shape of each graph for each of these functions. We'll start with linear. The graph of a linear function is just a straight line. Okay? It can be diagonal or horizontal. Remember, vertical lines are linear, but they are not functions. Linear equations can have a graph that's a vertical line, but again, these are not functions. Okay? For quadratic functions, remember these are the U-shaped graphs. They can open up or they can open down. The shape of this graph, this graph is called a parabola. Parabolas have exactly one vertex, which is the maximum or minimum value of the quadratic. Finally, exponential functions have a curved line graph that is always increasing and always decreasing. The function approaches a very specific y value, which appears on the graph as an asymptote. Okay? So by contrasting quadratics and exponentials, I see that exponentials are always increasing, or if it's decay, it's always decreasing and approaching a single numerical value, that asymptote. Whereas quadratics have pieces that are decreasing and they have pieces that are increasing. So quadratics have increasing and decreasing intervals, whereas exponentials just are increasing or just decreasing. Okay? So let's take a look at some graphs and see if we can determine what function type these are. Example 3, I notice that this function is constantly decreasing. Okay, it just keeps moving down, and it's also moving away from this finite y value, the x-axis, y equals 0. This function is exponential. For the next one, we've got a U-shaped graph. We've got a vertex at the bottom of the graph, our minimum. Both ends extend upward into the positive infinity direction, the positive y direction. This graph is a quadratic. For the third one on the right, this looks similar to the second one. However, this one opens down. We have a maximum point, which is a vertex. And again, both ends are going down in the negative y direction, approaching negative infinity. So this is a quadratic. Moving on, we have a diagonal line here. This is a straight line, and I see that it has a constant slope. So this is a linear function. Next up, we've got a curved line. This is constantly decreasing again, but now we're approaching, as we move to the right, we're approaching a finite y value, y equals 0. It's approaching this dotted asymptote here. This is an exponential function. And finally, we have a horizontal line. This is a straight line with a 0 slope. This is a linear function. In particular, the equation is y equals 2. All right, so the last way we're going to talk about today, go ahead and flip the page, is algebraically. So given an equation of a function, how can we determine what function type it is? So remember, all of the functions that we're studying in this course in Algebra 1 represent relationships between inputs and outputs. That's what a function is. And it's expressed as two variables, x and y. How these variables are related to one another determines which function type we're looking at. So let's talk about linear functions. Linear equations have a constant additive rate of change, which we call the slope. X values are directly proportionate to y values. We most commonly see these as one of the three forms that we've learned this year: slope-intercept form, point-slope form, or standard form, where slope-intercept is y equals mx plus b. Point-slope is y minus y1 equals m times the quantity x minus x1. And finally, standard form, ax plus by equals c. The important thing to note is that a linear function is a polynomial of degree 1. So the highest power for x is going to be 1. Quadratics, on the other hand, are polynomial functions of degree 2, where the input x is squared, or if the x has a 2 in the exponent. Okay? We see these in one of two forms: in standard form, ax squared plus bx plus c, or in vertex form, which is a times the quantity x minus h squared plus k. But in both of these examples, notice that we have a 2 in the exponent. This represents a quadratic function. And finally, exponential functions is when we have a variable in the exponent, or the input x is in the exponent. Exponential functions have a constant multiplicative rate of change, in contrast to linear functions where we have an additive rate of change. So Exponential functions have a constant multiplicative rate of change or a constant ratio, which is also sometimes called the growth factor or decay factor. We see this in the form y equals a times b to the power of x. So see that x, that input, is in the exponent. All right, so let's try a few examples and see if we can determine which function type each of these are. For letter A, we have y equals 3x minus 7. I see that this x has an exponent of 1. So that tells me that this is linear. This is in slope-intercept form. For letter B, here we have an x in the exponent. We've got 3 times 1/2 to the power of x. This is exponential. For letter C, here we have the highest power is 2. And so this is a polynomial of degree 2. This is a quadratic. We're squaring the input. Letter D, again, we have an x in the exponent, so that tells me that this is exponential. Next up, we've got a quantity x squared. So even though we're subtracting 4, we're still squaring that x. If we were to expand this out and put it in standard form, we'd have that x squared term. And so this is a quadratic. And finally, letter F, y minus 2 equals negative 3 times the quantity x plus 1. Again, the exponent here is 1. This is a polynomial of degree 1 or a linear function. The form of this linear equation is in point-slope form. All right. Go ahead and flip the page. I just want to summarize just some of the things that we talked about today. So verbally, we know the difference between linear, quadratic, and exponential functions because linear functions have a constant rate of change. The first difference is the same. Quadratic functions, the second differences are the same. And finally, exponential functions, the constant ratios are the same, or the ratios between successive y values. For a table of values, we can find the first differences by finding that rate of change between successive y values. If the first differences are the same, then we have a linear function. If the second differences are the same, then we have a quadratic function. And then if the ratios are the same, if we take the ratio between any successive y values, if that's the same, then this is an exponential function. Graphically, we see the constant rate of change for linear. It's a straight line. For a quadratic, we see that it's a U shape or it's that curved shape. And then finally, for exponential, it's also curved, always increasing or decreasing, and it approaches an asymptote. Okay? So these have been our notes here on 8.5 linear, exponential, and quadratic models. We're going to get a lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.